The concrete mixing and pumping plant is prepared. Pipelines are laid out to the site of the block and pumping is commenced, as we saw earlier, for the foundations below basement level. Once this operation has commenced, it will continue day and night until the block reaches its finished height of 30 feet above basement level. Vertical cables, each consisting of 12 high-tensile steel wires encased in a flexible metallic sheath, are cast into the block and are anchored in the concrete foundations. After the concrete has been allowed to set, a tensile stress of 100 pounds per square inch is applied to these cables. The effect is to apply a stress which is in opposition to that of the load which will be superimposed by the turbo alternator. The result being that the stress on the block is actually reduced as the heavy loads are applied. When the shuttering is removed, it will be seen that the block is composed of two separate units, which are bridged with steelwork, which will support the bottom half of the turbine casing. The space below is occupied by the condensers. The setting of the steelwork is an operation calling for very great accuracy. The condenser doors have been fitted to this machine, and work is also proceeding on the construction of the heaters. In the background can be seen the combined control room for the boiler and turbine operation. The 100 megawatt turbine has 16 high pressure stages. The low pressure end dividing into two parts, each consisting of 5 stages. The exhaust steam passes down the throating to the condenser below. The steam pressure at the turbine stop valve is 1,500 pounds per square inch and the temperature 1,050 degrees Fahrenheit. This is the bottom half casing and the arrangement of the stages can be clearly seen. The steam rotor is placed into position. This close-up shows the formation of the low-pressure blading. These blades will revolve at 3,000 revolutions per minute. After the steam rotor is installed and very accurately aligned, the top half casing is lowered into position and the completed unit is made ready to receive the electrical equipment. The stator for the alternator is delivered to site in its wound state. The rotor is also supplied in its wound state and has to be threaded through the stator casing and coupled to the turbine shaft. A protective plate is placed inside the stator opening to prevent damage. A roller is fitted to the inboard end of the rotor shaft. The protective plate will act as a support for this roller. The actual threading operation calls for absolute understanding between the crane driver and erector. One false move could cause a great deal of damage to both rotor and stator. The rotor, having been slung true and level, is advanced inch by inch into the stator until the slings are hard up against the casing. The roller and bearing plate now play their part. Whilst the outboard end of the shaft is supported on blocks, the sling is transferred to its new position. The inboard end now rests on the roller and is assisted by Sylvester gear. Threading continues slowly. A restraining block and tackle is fixed to the outboard end to prevent sudden movement. Farther and farther the rotor is advanced until slings can be fitted to both ends of the shaft. The special lifting beam now plays its part. The shaft is slung from both ends and held in position whilst the protective plate is removed. The bearings are then fitted and the machine boxed up. After this operation, the exciter equipment is fitted and the machine is made ready for service. Whilst the construction of the machine has been proceeding, work has also advanced steadily in the construction of the boiler house. The structure for the main building has reached a stage when delivery of the main components of the boiler can be accepted. This drawing shows the position of the main components, and the pointer indicates the flow of fuel and combustion gas stream. The first and heaviest component is the boiler drum. This drum weighs 90 tons and, as can be seen, is dispatched by road. The drum will take many days on its journey, and the full cooperation of the police is given, who shepherd the awkward load through the various towns and villages en route. On arrival at the station, the drum is delivered direct to the boiler house basement. Here it is maneuvered into position, preparations having already been made for unloading the drum, preparatory to hoisting it into position. The drum is designed for a steam pressure of 1,850 pounds per square inch. The time has been reached for lifting the drum into its correct position at the top of the boiler house, where it will be slung from the roof, being secured in position by special drum slings. The hoisting operation is a very slow process, and the drum in its final position will be 123 feet above the basement level. Platforms are placed in position on the boiler house steelwork in preparation for the bolting up of the drum slings. The last bolts are placed in position, and the drum is now ready to receive the boiler components. Work on the installation of the boiler tubes follows soon after the fixing of the drum. The boilers are of the fully radiant type and of the twin furnace design. The evaporative capacity is 830,000 pounds of steam per hour, the steam conditions being 1,600 pounds per square inch at a temperature of 1,060 degrees Fahrenheit. This is a general view from within the boiler house, looking towards the turbine house. The coal bunker outlets can be seen in the middle distance. Pulverized fuel is fed to the combustion chambers by means of 20 coal burners at the front of the boiler. These burners are arranged in 5 tiers of 4. 12 auxiliary oil burners are installed for lighting up the coal burners. The type of oil burner can be seen from this close-up, which shows a unit being tested before installation. After lighting the coal burners, the oil burners are retracted and shielding doors automatically close to protect the burners from the heat of the furnace. The scene now moves to the rear of the boiler house. The immense amount of coal burnt in these boilers would inevitably produce large quantities of grit and dust. To prevent this dust spreading over the surrounding countryside, electrostatic precipitators will be built. The precipitators will be located at the rear of the boiler house near to the stacks. The stacks and precipitators are both constructed of reinforced concrete, the base of the stack being supported on 209 piles which are driven 45 feet into the ground. Heavy reinforcing bars are used for the octagonal base of the stack, which has to support the enormous load of a concrete shell 425 feet high, whose minimum internal diameter is 23 feet. The first 80 feet of the stack is octagonal with a circular core, the minimum wall thickness being 3 feet. The two flue openings, which are 32 feet above ground level, are 28 feet high and 15 feet wide. The stack will have a mid-filler at 45 degrees to the axis of the flues. The interior of the stack will be lined with acid-resisting bricks. Looking down from the top of the stack can be seen the precipitators under various stages of construction. Here we see the foundations for the second chimney stack. The top 20 feet of the stack is built in special blue brick. Vertical gaps are left at about 7-inch centers, which each contain a 1-inch diameter rod, the rod being anchored into the concrete at its lower end. The upper end, which will pass through the cast iron cap, is screwed to receive nuts which will hold the cap secure. The rods are protected with Hessian wrappings and are heavily coated with bitumen, the gaps in the brickwork being filled with concrete. Lightning conductors are fitted to the cap on completion. Approximately 2.5 miles to the northeast of the site lie a number of disused gravel pits, which are to be used as a disposal area for the flue gas dust, which is collected from the precipitators by means of water ejectors. Underground pipes will be laid to convey the water and dust mixture from the ash pump house at the power station to the gravel pits. The coarse ash from the furnace hoppers is removed by high-velocity water jets and carried to the main sump, where it is screened, drained, and finally loaded into lorries for disposal. A bulldozer is used, where possible, to excavate the wide trench for the ash pipes. Six 14-inch cast iron pipes are laid in the trench, 4 to carry the ash and water, and 2 for returning water to the ash pumps. As the pipes are laid in the trench, they are fitted with Stanton bolted joints. The detail of the joint is clearly shown in the following scenes. After the joints are bolted up, they are carefully checked for tightness before backfilling is commenced. At the approach to the gravel pits, the pipes have to cross the main Ashby Road, and special precautions are taken to ensure that traffic is held up as little as possible. Work is carried out on one half of the road, which is backfilled and made good before the second half is disturbed. The ash and dust handling plant will have to dispose of approximately 1,000 tons of ash per day. The scene now moves to the front of the power station, where the two outdoor grid substations are progressing rapidly. Manufacture of the concrete supports for the connections and insulators is carried out on the actual site. Shuttering and reinforcing is prepared to suit the type of structure, and after final dressing down, will be equipped with insulators and fittings. When completed, the station will supply the national network at two different voltages, 132,000 volts and 275,000 volts, the latter feeding direct to the new supergrid. The rupturing capacity of the oil-immersed switchgear is 3,500 MVA for the lower voltage and 7,500 MVA for the higher voltage. Coal for the station is delivered by rail and shunted to the full wagon sidings. The layout will ultimately include space for 12 full and 12 empty sidings, although only 6 of each are constructed in the first stage. The complete station will burn over 7,000 tons of coal per day. The full wagons are drawn off to the tipplers, where they